Thank you, Gandalf, and thank you to the organizers for inviting me here at this really great occasion. So I will start traditionally with embarrassing Harold with some memories. So that seems to be the thing. So first time I met Harold, I don't know if he remembers me, I remember him. I was a kid, I was an undergraduate student, so this is the ancient era, and I was an exchange student in Göttingen for an Erasmus program. And instead of doing what usually people do during Erasmus, so going to parties, I was going to talks in mathematical physics. So there was this workshop, Courant Center workshop, QFT on non-commutative spacetime. And Harold was there, and I remember him very well because my friend Dorothea was getting her tenure track position in Göttingen, and Harold congratulated her publicly in a very nice way. And that was a small gesture, but I found it like really nice that people are so kind to each other in this community. So that was one of the things I thought were great about mathematical QFT, and that is one of the events I remember from my stay in Göttingen. So thank you, Harold, for this very nice accent. And then from there, I guess I made my decision to actually join this community. And the first time I came to ESI was 3 years later, so 2011. There was a workshop, Rigorous Quantum Field Theory in the LHC era, which was also very interesting. And that was 2 months before my PhD thesis defense, so I was already incredibly stressed. But it was still a great event, and since then I've been in Vienna many times, and we had a lot of very interesting discussions, and I enjoy coming here. And again, thank you, Harold, for being here and for making this happen. So without further ado, well, Harold, herzlichen Glückwunsch, alles Gute. I wrote a number here. I don't know if this is correct because it sounds really large. And Gandalf said you haven't changed, and I agree. So I'm not sure. I think one has to take off some numbers from here. Anyway, so coming back to the plot, I will take 1 more minute before I start talking about science and do a commercial break. Sorry about that. So some of you might know about the organization I'm currently the president of, which is International Association of Mathematical Physics. And talking about mathematical physics community, I think it's worth mentioning it here, since there are people from diverse areas of research in mathematical physics, mathematical QFT in particular. So yeah, we had a congress a couple of weeks ago, and some of you were there, some of you were not. And I would greatly encourage everybody to join because it's a good opportunity to network, to meet other people doing mathematical physics in slightly different contexts, and maybe learn something new and kind of branch out a bit from what you're currently doing. We have an online seminar which everybody can attend, whether you're a member or not. You can read more about our association on the webpage. And if you're interested in joining, this is the online form. Yeah, I think it's important to keep the presence of mathematical physics as a separate subject in the sense from mathematics and physics, because very often it's kind of pushed to the margin of mathematics and pushed to the margin of physics, and we don't really have a home. So it's good to keep some sort of network of people who identify as mathematical physicists. Okay, so please consider that. Enough of me talking about commercials. Now let's get back to actual science. So I promised to talk about perturbative and non-perturbative AQFT. This is probably wasted on this audience because everybody knows what's algebraic quantum field theory. But if there is one person who doesn't, it's worth saying again. So what I'm working in since, essentially the start of my career is the general sort of algebraic approach to quantum field theory, and it goes back to Haag and Kastler, and the idea is that you describe a quantum field theory by specifying algebras of observables that you assign to, well, originally it was bounded regions of Minkowski spacetime, and then you want, when you go to a larger region, you want the algebra of the smaller region to be contained in the algebra of the larger region. So this way we obtain a net of algebras. And then there are some axioms, and I'm going to name two axioms that are important for what I want to say in this talk. So one is the causality axiom, which means that observables that are assigned to space-like separated regions commute. And then time slice, which says something about dynamics. So if we have a neighborhood of a Cauchy surface in a given region O, we usually like drawing that, so let me draw a picture. So if we have a region O, and then we have a Cauchy surface here, neighborhood of a Cauchy surface N, then the algebra of this neighborhood of the Cauchy surface is already the same as the algebra of the whole region. So this is the meaning of the time slice axiom. Okay, there are more axioms in the Haag-Kastler framework, but they are, I mean, many of them are related to the vacuum, existence of the vacuum. I'm not going to talk about that. So let's stay with these two because they have the essence of what I want to say next. And yeah, I mean, constructing those models, I mean, the conference is called exactly Solvable Models. Well, constructing those models is A, difficult, B, people have been doing for a long, long time, and I know that Harald has contributed a lot, and there's this wonderful model of Harald and Reimer that might be the first interacting QFT in 4D, fingers crossed. But the problem is that constructing models of interacting QFTs satisfying, well, Haag-Kastler or any other sensible axioms is hard, okay? And I think we all agree. And this is not the reason to give up. Well, there are various ways of approaching it, and here is a slightly newer perspective, which focuses on the algebraic structure and then pushes away the question of constructing the vacuum for later. So there is a proposal by Buchholz and Fredenhagen from 2020 about just the question of how to construct the net of C-star algebras for interacting theory, not discussing the question of existence of states of certain kind, just algebras, okay? And I think this is already, well, it is progress in terms of understanding the algebraic structure, and maybe will allow us to study some general properties and structural results in the future. So I'm going to talk about that approach. And the main idea here is that we obtain an abstract C-star algebra for each region, which is generated by a collection of unitaries with a number of relations. Very simple, actually, I will give them explicitly. And these unitaries are physically motivated, interpreted as local S matrices. So, and they are labeled by local functionals that have physical interpretation of interactions. So it's kind of based on Lagrangian framework, which I'm going to talk about later. And it is motivated by perturbative algebraic quantum field theory, which I have been working on as well. So there are a lot of lessons that we learned from the perturbative approach. You can think of this as a non-perturbative formulation that kind of feeds on that. And well, I think there's nice synergy of these two approaches. Okay, so let me go into the detail of that story. First of all, it works on things more general than Minkowski, so we can construct models on the whole class of spacetimes, which are of a particularly nice type, namely globally hyperbolic. So there is a Cauchy surface, well, like that one there, and it is a sort of analog of having a model where you have well-posed initial value problem in the classical theory. Then we have a configuration space, which is the choice of objects we want to study. So scalars, vectors, tensors, whatnot. And mathematically, this is a space of smooth sections of some vector bundle over M. And here are examples: scalar field, smooth functions, Young-Mills with trivial bundle, the algebra valued one forms, effective quantum gravity. If you go far enough, then covariant two tensors. And yeah, because I don't want to really specify the theory for now, I would just use the notation phi to mean an element of the configuration space, whatever it is. And then dynamics is specified using the Lagrangian formulas. Okay, so let's start with the classical story. So we consider observables modeled as functions on the configuration space, and for, well, mathematical convenience, I assume them to be smooth. And just because everything from now on is going to happen on the fixed spacetime, I'm going to drop M from the notation. And if I'm using different spacetimes, I will give you a warning. So now I want to assign these algebras, these, well, we don't have a product yet, but these observables to regions, okay, in spacetime. So I need to be able to localize them somehow. And this is done by the notion of a support. So a support of a function like that is essentially the region of spacetime where this observable, this function, is sensitive to changes of the field configuration. And here is the formal definition. So set of points in M such that for all neighborhoods you can find phi and psi. Psi is supported in that given neighborhood such that F sees the difference between F of phi plus psi and F of phi. In particular, there is a nice subclass of well, functionals that I will use, which is that of local functionals, and they are essentially of this form. So depend on the value of field and its derivatives at a point integrated over the whole spacetime. So this is what people usually use in physics. Okay, so now dynamics. So for this, I need a Lagrangian. Here there is the word generalized Lagrangian. This means, well, essentially a Lagrangian with a cutoff. So given a Lagrangian density, I can construct a function from the space of test functions, so cutoffs, compactly supported and smooth, local functionals, and here are the examples. So the generalized Lagrangian is this map that takes a cutoff and spits out a local functional. Free scalar field, right? So this is the usual Lagrangian density times cutoff. Young-Mills, again, similar structure. And here, Einstein-Hilbert action. But you can use other ways of well, smearing this with a test function as well, and sometimes it's useful to actually use other methods. But I'm not going to talk about it right now. This is a simple example. There is an easy way of making a generalized Lagrangian out of any local functional. Namely, you take your functional and then evaluate it at, that should be the curly phi. You evaluate it at a point phi multiplied with your test function. So that also gives something that depends on this cutoff in a nice way. And yeah, because this is such an easy and straightforward prescription, I'm going to essentially not distinguish between generalized Lagrangians and local functionals, because any local functional can be made into a generalized Lagrangian. All right, so I will just write F instead of LF to denote that object. Right, so now we need some dynamics, and it works as follows. So first of all, we have this cutoff, so we have to do something which is independent of the cutoff. And first I construct a finite variation here. So I perturb my field configuration. Maybe the word perturb is suggesting something infinitesimal. No, this is just adding a given compactly supported configuration to my configuration phi and subtract the original L of f of phi. And then I choose f such that it's 1 on the support of psi. Interestingly enough, that whole object, because of locality, does not depend on this choice of f. So on the left-hand side, you see I don't have f anymore because this difference doesn't depend on the choice of f. So this is the finite perturbation that will come up later on as well. And then Euler-Lagrange derivative is just infinitesimal version of this. So what I do, I multiply it with some parameter, then take 1 over t. This is the difference quotient that we all know from calculus. Take the limit, and this gives me essentially the formula for the variational derivative, right? And then, as I said, f to 1 on the support of psi. Here, I only have the usual Euler-Lagrange derivative from the variational bicomplex as the thing multiplying psi. And the field equation, as you might expect, is the condition that this object is 0. Now, another way of packaging this, I use the notation dl. This is not a coincidence. I want to emphasize that this object here, dl, is a one form on the configuration space. So geometrically, the space of solutions of field equation is the 0 locus of some one form obtained from the Lagrangian. So that's the classical dynamics. So now I want to package this into some data for my C-star algebra. So first of all, I'm going to do things in a sort of covariant way. So I will, well, essentially have background structure, which will be a pair of a spacetime, background spacetime, and a background Lagrangian. So the way one wants to think about it is that we have a given theory with a given Lagrangian on a given background spacetime, and now we are thinking about possible deformations of that theory by adding different terms to the Lagrangian. So there is some background Lagrangian to be considered, and it, well, I mean, we assume a particular form, namely the kinetic term gives us normally hyperbolic equations of motion, normally hyperbolic operator, and there is some nonlinear, sorry, higher than quadratic term, V0, which then doesn't contain derivative higher than 1. So it could be polynomial of arbitrary degree, but we don't want to spoil this nice hyperbolicity. Okay. So then we consider all local functionals that we can add to this, and well, essentially, again, don't ruin the hyperbolicity of the equations of motion. And these are the interactions. And well, int ml is the space of possible interactions that I can add to L. And yeah, they could be thought of as perturbations or deformations of the original theory. So now let me define that C-star algebra, and I promise it was straightforward. It is straightforward. So it's the C-star algebra freely generated by unitaries S of F with the condition that for a constant C real number, this has this particular form. So this kind of fixes normalization in a sense, and then relations. Okay, so we want to introduce relations. First and foremost, there is the locality or Einstein causality relation, which is the relation that guarantees that well, the first of the first of the Hag-Kastler axioms is fulfilled. So we have commutation at space-like distance. So this is encoded in this nice property. So we have S for a sum of 3 functionals, and then such that F and H have disjoint supports, and then this factorizes nicely in this way, independently of what G is. G could be whatever. And then there is dynamics, and dynamics is here described in terms of this finite difference I have defined before. Here I introduce also a notation for a shifted functional, where I shift by psi. So the relation is that on the right-hand side, well, this is an on-shell relation. So when equations of motion are satisfied, on the right-hand side, I have a shifted F, and then this finite difference, and that I identify with the original S matrix. This, if you remember your first QFT course, if you ever had one or read a book on the subject, this is the Schwinger-Dyson equation in a sort of unitary form. And the Schwinger-Dyson equation is related to, well, how the path integral measure changes, well, under translations, essentially. So here, the fact that you have this delta L is related to the fact that this S matrix should model something that sits under the path integral, and then you have to shift both F, which is a sort of interacting part of the measure, and L, which is the Gaussian part of the measure. So that's heuristic, but maybe I will make this even more explicit in the perturbative setting. Okay, so these are the first two that well, there's one more these days, but I will come back to it later. So let me now say how this whole thing arises in perturbative AQFT. That whole thing makes sense there and has a very explicit realization, because you might be uncomfortable with the fact that, okay, there's this huge abstract C-star algebra. It doesn't have anything to do with reality. So this can be thought of as explicit realization, but in perturbation theory. So let's go. Here we assume that our background is quadratic, so can be quantized exactly. And it leads to normally hyperbolic equations that I want to denote this way. So P is a normally hyperbolic operator. And this equation has distinguished green functions, retarded and advanced green functions, and their difference is the commutator function. And then we add to it a symmetric part, and then we obtain something known as the two-point function of a Hadamard state, provided that this H is a solution by solution to P. This thing has to be of positive type, so that it deserves the name a two-point function of a state, and nice singularity structure. So it should look like a two-point function of, well, the Weidmann scalar field in Minkowski. So there is a wavefront set condition on that guy. Okay, and we also have something that well, is an analog of the Feynman propagator, where we change the sign between retarded and advanced, and we still have this extra bit from the symmetric part. So these two objects, W and delta F, are then used to construct some algebraic structures. And okay, so let's do some explicit definitions. So we can construct a bidifferential operator where we take derivatives with respect to fields and then contract with the Feynman propagator. And this has a nice sort of graphical interpretation. So I can think of it as having the Feynman propagator assigned to an edge, and then derivatives at the vertices. And then I'm applying this to some collection of local functionals. So I can think of applying this to well, functionals that corresponds to, let's say, polynomials, like this one or this one. And then the combinatorics of that formula is familiar to everyone who has studied quantum field theory, corresponds to Feynman diagrams that you obtain by, well, essentially contracting such external legs with the Feynman propagator. Okay, and sometimes some legs remain on the loose, and that corresponds to remaining factors of phi in your formulae. So without maybe going too much into the details, where this is essentially a sort of closed formula for what I'm doing here. Yes, Anton. Oh yeah. So in the first go, I want these to have disjoint support. Yes, correct. So this formula is well defined as it stands if the supports are disjoint. Now, as Anton said, there are singularities lurking behind the corner. So if I want to extend this to arbitrary support, which I do at the end of the day, then I need to use renormalization, and the choice of renormalization here, convenient choice, is Epstein-Glaser. So it's a sort of story of extending certain distributions to, well, that are defined everywhere outside of total diagonal to distributions defined everywhere. Again, maybe the technicality is not that important, but it is a prescription to extend those n-fold time-ordered products of things with disjoint support to things with arbitrary support. Okay, so put it in the black box, you get an appropriate time-ordered product. And then in that process, you require certain properties, certain axioms that these Tn's have to satisfy. This is part of this Epstein-Glaser story. And the important one is the causal factorization property. So if you have a bunch of these arguments with supports that are all not later than the other bunch, so that you can, again, I'm going to redraw a little picture. So you have a bunch of things here, and you can somehow separate it, or they can also intersect from a bunch of supports here. Then this time-ordered product factorizes. So there is the time-ordered product of one bunch, and then you start with the other, where this star product is obtained by a similar formula, but with W instead of delta F. I think I had it. I have it before. Maybe I didn't, but yeah. So this star product is defined similarly to this, but you replace delta F with W. Okay, so then the main idea of Epstein-Glaser is to demonstrate that such a family exists, okay, but it is not unique. And this is not a surprise if you are working in quantum field theory, because we know that there is some renormalization freedom. This non-uniqueness corresponds to renormalization freedom. Spoilers. But all right, so let's say we have one family like that, and then we define the S matrix. So the name S here is not a coincidence, as a time-ordered exponential, essentially. And then this S matrix satisfies this now hopefully familiar property that I postulated for those abstract unitaries in the C-star algebra of Buchholz and Fredenhagen. So this is the relation that we get for S matrices constructed perturbatively in perturbative algebraic quantum field theory. Okay, and we can also define, well, gather all those Tn's and define an operator on multi-local or multi-local, so products of local functionals. And a sort of a direct interpretation of that object is convolution with Gaussian measure in the path integral. So This correspondence is formal because the right-hand side may or may not exist in, the measure theoretic sense, but the left-hand side is a well-defined differential operator with coefficients that we obtain via Epstein-Glaser renormalization. All right, and then we also have the corresponding time-ordered product, which is defined like this. So there is essentially a twist of the pointwise product by this map T. I'm missing a bracket that should not compile. So S of V, now this S matrix can be now literally written as the time-ordered exponential. Okay, so these are, the shape of it, right, is I V over H bar, exponential I V, V is real. So it obviously looks like something that should correspond to a unitary operator if we're on the right track. And then these abstract unitaries from Buchholz and Fredenhagen C-star algebra are supposed to correspond to these objects. All right. Yeah, okay. So if you were wondering why T is the time-ordered product, well, here's the explanation. So your star, your quantum product in your algebra, this is actually the thing that is well-defined regardless. If the support of F is later than the support of G, then these two coincide. And if there is a swap, so G is later than F, then the order changes. So that you think about the star product, you order it in time, and then you get the time-ordered product. Okay, so let me now do a bit of interlude. There are situations where all these things actually converge, so where you can do a bit better than formal power series. And integrable models were mentioned before today, so I'm going to mention one that I worked on with Dorothea Banz and Klaus Fredenhagen, the sine-Grodon model. So we applied this machinery, this a priori perturbative machinery to that, and then we showed that things actually nicely converge. So here V is taken as the cosine. There is the regime in which we have proven the convergence. So this is sort of this beta in the interval of 0 to 1, meaning that the model is finite. So this is the best case scenario for the sine-Grodon. And then we have shown that the S matrix converges as a functional on the configuration space. So everything is nice. We constructed relative S matrices. I didn't talk about that, but they're related to the notion of interacting fields. And then in a later paper with Fredenhagen, we have also shown that one indeed gets a local net of von Neumann algebras where, we have also a family of Hadamard states, which are good for that particular application. Yeah. Yes. Yeah. Yeah, so after that, so then there is a regime where, so best case scenario, it means that you expect things to converge and be finite. Then there is super renormalizable bit where you expect things to, need only finite renormalization. And then there is, I don't know what's happening bit. Yeah. Oh, this, okay. But, yeah, so I'm talking about the algebra, okay? Yeah. Yeah. Yeah, that question doesn't have an obvious answer. it's somewhat open. So here the class of states we use. So we have the vacuum for So you imagine this sine-Grodon as a perturbation of the massless scalar field in 2D. Okay, that doesn't have a vacuum state. So instead, there is a class of Hadamard states that are essentially vacuum minus the zero mode. But this is not a unique thing. There's a whole family of those. So this net of von Neumann algebras is constructed in, well, one hence all of such states, because these are locally normal, so they are in a sense equivalent. And then these are also locally normal to the massive vacuum, so you can imagine the situation where you shift a bit of like the quadratic term from the cosine to the free part, and then you have like a mass. So this is what we have done. Now, we have not studied like particle excitations of that. So we have not studied states that correspond to these various particles. Part of it is that it would be desirable to have the proper interacting vacuum for that model. I mean, this is, you know, an operator algebra. You can construct states, but we have not succeeded yet. Actually, I mean, honestly, I'm not working on this at the moment, but Dorothea was working on this for a while, but we have not succeeded yet on constructing the interacting vacuum. And when we do, we can answer your question. But I think it's an interesting question to answer, and I hope that we make some progress. Yeah, but thank you for mentioning that. But anyway, so this is a nice example of where you can actually take this perturbative story seriously. Yeah, so coming back to the plot, well, there is this question of renormalization I mentioned before. So there is a non-uniqueness in constructing T's, and this is governed in the perturbation theory by Stickelberg-Petermann renormalization group. So these are essentially maps from formal power series in local functionals back to formal power series in local functionals that satisfy a bunch of conditions that kind of guarantee that when you pull back the S matrix through such maps, you get another S matrix. I will list those conditions in a second. And then there is the main theorem of renormalization, which says that any other legit definition of time-ordered products, call them T tilde, arises by pulling back, say, your original choice of T by one of those maps in the renormalization group. So renormalization group, in the sense of Stickelberg-Petermann, completely characterizes the non-uniqueness of time-ordered products. So that's great. And physically, it corresponds to adding finite counter terms which change values of couplings, because, well, given choice of T is already renormalized. This is post-regularization and subtraction and whatever you do. This is renormalized, but then you can change the values of couplings because you have renormalization freedom, and this is what that Z does. Okay, so now non-perturbatively, we can also formulate this idea for the Buchholz-Fredenhagen algebra, and this part is based on my paper with Brunetti, Ditch, and Fredenhagen, where, well, it was essentially about quantum little theorem. So the idea was to study symmetries, but we ended up also studying type slice axiom and renormalization. And in that paper, we formulate this concept of a renormalization group. So again, these are now bijections of, no formal power series, just bijections of the space of local functionals. We require compact support preservation. Again, locality, it appears, so that we get locality also for S matrices. There is a dynamical relation, which essentially says that Z preserves the dynamics. There is a nice behavior under the field shift. The general formula is a bit dense, but for the, well, simple case of quadratic action, this just means that Z is invariant under shifts. Pretty simple. And it's not supposed to change the causal structure. So we want to keep that. Okay, so these are the properties. And again, well, this acts on your C-star algebra by acting on these local functionals. All right, so I I started late, so what, how, 5.5, great. So I can say something about symmetries and the sort of original motivation for the paper I mentioned. So there we looked at the n-component real scalar field. So this is the configuration space. Asymmetry transformations are essentially the affine local gauge transformations and the diffeomorphisms, compactly supported diffeomorphisms of M with the product defined as follows. So you can do your homework and see how these act. Well, no, this is, sorry, this is, the word gauge is loaded. This is this particular group. So these are, these are compactly supported functions on M valued in affine transformations. So these are just affine transformations. So you're in the like n component real scalar field. So you can mix up these components. That's essentially what you can do. Yeah, maybe call it, well, yeah. Some people might call it gauge transformations, but I understand. Yes, yeah, maybe the word symmetry is also confusing. These are symmetries of the configuration space, not of your dynamics. So yeah. So I don't require the concrete Lagrangian to respect those symmetries. Yeah, thank you. Okay, so this acts on local functionals by a pullback. And then there is a fun thing that appears here is a L, so L is the background Lagrangian, L-dependent action of G, where you pull back a functional and add also this term which corresponds to the change of L under my gauge transformation. And then this, okay, so then the interesting question here is how the theory, the quantum theory, behaves under these transformations. So how these S matrices and so on behave under these transformations. And in perturbation theory, there is a similar situation which is described by something called master word identity, which then, well, in the strict form, it guarantees that classical symmetries remain unbroken. But there is also anomalous master word identity, which tells you how much they are broken. So what we have done in this paper was to find an analog of that in the C-star algebraic setting. And then we realized that, well, this how much things remain broken is related to renormalization. So what we introduced was a family of maps from this group of symmetries of the configuration space to the renormalization group, satisfying this co-cycle relation. So these will be important. So the set of such co-cycles, okay, are denoted by Z of ML, and these allow us to formulate the unitary anomalous master word identity. Let's see what it does. So I pull back the S matrix through a given symmetry, and then in a particular representation, I want to know whether this can be described by pulling back by some renormalization group element given by my co-cycle. And then if this is possible, then a representation pi, I would say that satisfies the unitary anomalous master word identity. So this is, in a sense, condition on the representations. And then I can, well, look at all representations that do that and, well, construct an ideal, which, okay, depends on this co-cycle now. Take a quotient of my original C-star algebra and get something which can be thought of as generated by elements of this form. So well, generators of the previous algebra plus things in this ideal. Okay, so there is also interesting interpretation of this co-cycle evaluated at 0 that sort of in perturbation theory, if we go back, this corresponds to, well, in path integral, this corresponds to the logarithm of the Jacobian that corresponds to that symmetry transformation G, and the infinitesimal version is actually related to renormalized BV Laplacian. So this is something I studied independently in the perturbative context. And there is a paper I didn't mention, which makes that connection a bit more precise, which is a paper of very long title, again with Brunetti, Ditch, and Fredenhagen, West-Domino consistency condition, BV formalism, and L infinity structures. It takes 2 lines to write that title. Okay, I think that is my time up. So thank you for your attention. And again, happy birthday, Harold. Thank you.